Yeah, so you welcome to lesson 3 of the structural steel design course. And in lesson 3, we'll be taking practical examples of the design of bolted connections. So I'll be showing to you how we go about the design of bolted connection from all that you have learned in the previous sessions, and then we would apply them in this video. All right, what you can see on my screen basically is the single cover butt joint. All right, it's a method of joining steel plates together. All right, we have the single cover butt joint, and also we have the double cover butt joint. Now, as you can see, the single has a plate connecting two other plates. Then the double cover butt joint has two plates, one above and another below, making it as though the connected parts being in between the two plates. Now, the implications of these two types of joints, or these two different kinds of joint that we have here, is that the single cover butt joint usually results in a single shear failure, and that's what you're seeing on the right part of the page. While the double cover butt joint usually results into a double shear failure. All right, so if you see what we have here in figure A, figure A shows the single shear failure. That is, the bolt will only shear in a single plane. All right, so when the forces tend to draw out in tension the plates, all right, so it will tend to cut the bolt in shear, and that's exactly what you're seeing here. So, and in double shear, you see that it tends to cut through the bolts in two different shear planes. All right, now for the bearing failure, I said earlier that there are two possible failure modes, or two major possible failure modes with your bolt connection. One is that it fails in shear, and also it fails in bearing. Whichever is the least or smaller, that's the strength of the bolt, and that's exactly what we're going to be using. So you see that bearing failure happens when the hole is slightly larger than the bolt, and the bolt is loosely placed in the hole. So if the connected plates are made of high strength steel, then failure of the bolt can take place by bearing of plates on the bolt. So you can see how bearing occurs here. It tends to bend and take the bolt out of shape due to the largeness of the hole in relation to the diameter of the bolt. All right, so it's time to solve some examples. All right, so I'd like that you go along with me as we take some examples. So we have our first example here. It says a lap joint between plates 65 mm by 8 mm is shown below. It transmits a factored load of 45 kN using black bolts of 16 mm diameter and grade 4.6. The plates are made of steel grade S275. Now we are supposed to check the shear capacity and bearing capacity, and also we are supposed to calculate the number of bolts required to make the connection, and also we are supposed to find the pitch and edge distance. All right, so this diagram, as you can see here, this figure rather, you can see that it aligns with one of the two joints I showed earlier, and this would align better with the single cover butt joint, but this has no cover. It's just a lap joint. This is not a butt joint, this is a lap joint. The reason why I said it aligns is because this failure mode is also going to be a single failure mode. All right, a single shear failure mode. It looks more like a single butt cover joint, however it is not. This is a lap joint, but it has a single shear failure mode. So what implication does that have in our design? We're going to see as we go ahead. So the first thing that we are supposed to calculate is the strength calculation. We want to determine the strength of that joint. All right. Okay, so the first thing we are going to do is to identify the information that we have been given. So we understand that the diameter of the bolts that we are using in this situation is 16 mm. However, the standard clearance hole diameter is supposed to be identified. So if you check your BS 5950, check for table 36. This that you can see, table 36, standard dimensions of holes for preloaded bolts. So you see standard clearance hole, which is the second column, standard clearance hole. You see that we are not using oversized hole, we are not using short slotted hole, we are not using long slotted hole, we are using a standard clearance hole. All right, we have the nominal diameter, the one we have been given in the question, but then we have to create a clearance hole, standard clearance hole. You would discover that the difference between the nominal diameter and the standard clearance hole is a difference of 2 millimeters. 2 millimeters, 16 to 18, 2 millimeters, 20 to 22, 2 millimeters, 22 to 24, 2 millimeters, 24 to 26, 2 millimeters, until it is greater than or equals to 27. Then we have 3 millimeters. You see that now. So how does this affect our work? So we are going to have the standard clearance hole diameter. Then this one is a capital D, all right, which is 16 plus 2 mm that I spoke about, and that will give us 18 mm. All right, now I told you earlier in the previous session that the strength of any connection, bolted connection to be precise, can be either in shear or bearing. Shear or bearing. So whichever is smaller, whichever of these two is smaller, then that's the strength of that connection. All right, so to start with, let's check for shear. So for shear now, let's determine the shear capacity. Let's call this shear capacity. let's call it shear capacity. Let me erase this. Okay. All right. So from our clause, from clause 6.3.2 that I referenced in the code of practice, clause 6.3.2, which speaks about the shear. 6.3.2. So this is 6.3.2. You see, this shear capacity. Now the shear capacity can be obtained or should be taken as PS is equals to PS AS. We're coming back to this, but first let us import our formula. We have PS is equals to PS AS. Now from our definitions, you see that AS is the shear area, while the PS is the shear strength as obtained from table 30. So the shear area is defined in 6.3.1. So let's check for 6.3.1. You see that above here. Bolts may have short, standard or long thread length or have fully threaded shank. The shear area AS of a bolt should normally be taken as the tensile area AT. Did you see that? Tensile area AT as specified in the appropriate bolt standard for bolts without a defined tensile stress area. AT should be taken as the area at the bottom of the threads. You see that now? So we are going to look for the tensile stress area for 16 mm bolts of this particular grade 4.6. Let me write that so that it can be clear enough for you. For 16 mm diameter bolts of grade 4.6, all right, tensile area AT would be equals to 157 millimeters square. This is obtained, you can get this from the steel designer's manual, the one I gave to you earlier, and for reference purposes you can check page 1253. all right, now what of the shear as shown in page 30 of the BS 5950? Now look at it here. The shear strength PS is obtained from table 30. So let's look for table 30. Where is table 30? Now on table 30, both grade 4.6 has a shear strength of 160 Newton per millimeter square. You see that? So we import that to this 160 Newton per millimeter square. So PS 160 Newton per millimeter square. This is obtained from table 30 of BS 5950. Okay, so we have PS to be equals to 160 multiplied by 150, and that should give us 25.12 kilonewton. You see that now? So that's for the shear capacity. Let's check for bearing capacity, just like I've said earlier. For bearing capacity, we picked this from clause 6.3.2. all right, for bearing capacity we'll pick it from clause 6.3.3.2. so let's check that from our code of practice. 6.3.3.2. so you see this now, bearing capacity of bolts. The bearing capacity of bolt itself should be taken as PBB is equals to DT subscript B P subscript BB. So let's get that into our calculations. So we have PBB is equals to DB T subscript P and PBB. all right, so what do we define this as? I've visited this in our previous lessons, but for remembrance sake, what do we define all of this as? All right, so we have the D to be nominal diameter. You see that this time is nominal diameter, not the standard clearance diameter. all right, PBB is the bearing strength of the bolt, and we can obtain that from table 31. On table 31 for grade 4.6, the bearing strength is 460, and T subscript P is the thickness of the connected path. all right, so we can use that as we go. Now the D is the nominal diameter, of which we know to be the nominal diameter is 16. The thickness of our plate is 8 mm, and then the PBB is 460 as we have shown earlier. So this should give us 58.9 kilonewton. all right, so we've done this. We have the bearing capacity. This is the bearing capacity of bolts. all right, of bolts. Please note that the bolt bearing capacity. So this we are looking next is the bearing capacity of the connected parts of plate, which you can also call the connected parts. all right, so from our formula under the clause 6.3.3.2, let's look at what it says there. 6.3.3.3. so the bearing capacity of connected part is PBS is equal to KBS DTP PBS, but PBS should be less than or equals to 0.5 KBS ETP PBS. all right, so we're going to check for everything. E is the end distance, PBS is the bearing strength of the connected part. See table 32. You see table 32 shows to us that for S27 grade, S275 grade that we're working with, the bearing strength is 460, and the KBS for both in standard clearance hole, which applies to us, is 1.0. Okay, so let's apply that. Let's bring in our formula first. PBS equals to KBS PBS dBTP. See that now? All right. So to fill in this, KBS as I've shown to us is 1. PBS as I've shown to us is 460. dB, which is the diameter of that bolt, nominal diameter, right, is this, and thickness of plate is 8. Okay, so we'll have the same thing as above, 58.9 kilonewton. Okay, so that's for the connected part, but we're being told that whatever we get here must be less than or equals to, let me put it properly, this must be less than or equals to 0.5 KBS E, which is the end distance, TP PBS. So we have to confirm that this holds. We have to confirm that. All right, so to confirm that, we'll have 0.5 multiplied by 1 multiplied by the end distance, and the end distance in this case is 35. If you check this, let me point it out to you. If you check this, oh my, sorry about that. You see that the end distance here is 35 from here to here. That's exactly what it's talking about. All right, okay, so to continue, we have multiplied by 1 and multiplied by the end distance 35, thickness of plate 8, and PBS is 460, and this automatically gives us 64.4 kilonewton, which reveals to us that this is greater than this. So it still obeys that rule. All right, so we have been able to obtain the shear capacity and also the bearing capacity of this joint, or of the bolt and the connected parts. So if you are supposed to pick out the strength of this joint, you are going to look for the least of these values, and that's going to be the strength of that joint. Okay, so we have 35.12, we have 58.9, we have 64.4, whatever it is. So this would be the strength of the joint, 25.12. all right, so the strength of the joint, so let's put strength of the joint, that's 25.12. now, but you discover that there are 2 bolts there. We're not told that there are 2 bolts basically, but we designed this for, this value was obtained for a single bolt. Okay, this is single bolt, so we are looking for how many bolts now, because the question says calculate the number of bolts required to make the connection. So if this is the strength of the bolt, we have to look for the number of bolts that is slightly above this, all right, and that would be able to sufficiently support that joint. I hope you've been able to get me. All right, so this remains the strength of the joint, but we need to know the number of bolts that will keep this joint in place as against the tension that is subjected to, or the force is subjected to. So it's been subjected to a force of 45 kilonewton. All right, if you look at this here, we have 45 kilonewton here, and then here 45. So we need to know how many bolts will be able to keep this position in place. All right, knowing full well that a single bolt has this strength. All right, a single bolt has this strength. Maybe I should safely say it this way. It's going to help your understanding strength of the bolts of a single bolt. Let's put it like that. Of a single bolt. Strength of a single bolt. Okay. So to get the number of bolts, what we're going to do is to divide the tension or the force by the strength of one bolt, which will tell us how many is required in this case. This gives us 1.79, so it will be safe to say 2 bolts. So the number of bolts required in this case is 2 bolts. So we've been able to obtain the shear capacity, we've been able to obtain the bearing capacity, and then we've been able to calculate the number of bolts required to make the connection. So we're supposed to find again the pitch and the edge distance, and that will be all. And to do that, it's a very simple procedure, a very simple procedure. Okay, so I believe that you might have gotten what I have here. So permit me to do a little cleaning. Let me rub off what I have here. Okay, so to have my pitch distance, all right, for the pitch, which you may also call the bolt spacing. You can also call it the bolt spacing. Okay, so we need to check clause 6.2.1.1 for this information. All right, so when you go to your code of practice, you see clause 6.2.2.1, clause 6.2.1.1. Yes, you see that bolt spacing. Then we have the minimum spacing. So the code says for standard clearance hole or holes for fitted bolts, the spacing between centers of bolts should not be less than 2.5D. You see that that's the minimum. It should not be less than 2.5D. So you see that the minimum spacing there, the minimum pitch distance the minimum pitch or both spacing is 2.5 D. And be mindful, please, it is the small d. It is the small d. Okay, so we have 2.5 multiplied by 16, and that should give us 40 mm. So we have also the maximum pitch. And this, you may want to check the clause next to that, clause 6.2.1.2, which says the maximum spacing in unstiffened place should not exceed 14 T. It should not exceed 14 T. All right, so and T is the thickness of the thinner element, so 14 T. So we have 14 multiplied by 8. That should give 112 mm. All right, so it means that whatever pitch you are providing should be such that 40 will be less than or equals to the pitch, and the pitch will be less than or equals to 112. So the pitch here that is provided, we can provide 50 mm. It will be correct, and that's why you're saying 50 mm right below the question. All right, so we've been able to also look to the pitch distance. Now let's consider the edge distance, and that will be all. The edge distance. So you need to check clause 6.2.2.4 and 6.2.2.5. Okay, so that you not get this model together. Okay, so the minimum distance, minimum edge distance, is 1.25 D, and this time is a capital D. Capital D. In case you're not seeing it, let me show it to you. 6.2.2.4. If you see this table with the maximum edge distance, maximum edge or end distance, you see. So the table says minimum edge and end distance of both. For a rolled, if you remember what I told you about the rolled in the first lesson, machine flame cut sun or plain edge or end, the edge and end distance is 1.25 D, and that's exactly what we're using, 1.25 D. Okay, and that should give us 1.25 multiplied by 18. That should give us 22.5 mm. So the maximum edge distance according to that table, 11 T epsilon, 11 T epsilon, and that's 11 multiplied by 8 multiplied by 1, and that should give us 88 millimeter. So this is the minimum and this is the what maximum. It means to say that whatever edge distance you are providing should be such that 22.5 should be less than or equals to the distance, and the distance should be less than or equals to 88. That's what we're talking about. So maybe you have a question on what the epsilon or how the epsilon equates to be 1. All right, that's a simple one. The formula for to obtain epsilon, this is what I mean by epsilon. This is 275 over the strength of steel raised power 1/2. And in this case, you see that we are using 275 grade, so automatically it becomes 1. We are using 275, so we have 1. So that's how we obtained that. So if you have any further questions as to all that I've shown you in this lesson, please do well to reach out to me and I'll be well pleased to answer you. All right, so see you in the next lesson. Bye.